Welcome to a deep dive into artificial neural networks.
Those brainy systems
Yeah.
behind self-driving cars and personalized music recommendations.
Yeah, you guessed it.
You're curious about this year's Nobel Prize in physics, right?
Okay.
And how it all connects.
Yeah, how does it connect?
Well, it starts with physics.
Okay.
Physics inspired the foundation of these powerful networks.
Really?
We're going to dive deep into the work of the laureates,
Okay.
John Hopfield and Geoffrey Hinton,
All right.
to uncover those fascinating connections.
I'm excited.
This story takes us on a journey through biology, computer science, and physics.
Wow, a lot to unpack there.
It really does show how different fields can come together to spark a technological revolution.
That's what makes it so fascinating.
Yeah.
Okay, so imagine this.
Okay.
It's the 1940s, the dawn of the computer age.
Okay.
We're talking massive machines
Huge.
designed to crunch numbers.
Yeah.
Like cracking codes during World War II.
Right?
Not exactly the AI we picture from sci-fi, is it?
Not quite, but things started to change in the 1950s.
Oh, really? How so?
Scientists began asking, can we make computers think like us?
Interesting.
They were fascinated by the human brain's ability to recognize patterns.
Yeah,
Something computers just weren't wired to do.
makes sense.
Right.
Our brains are constantly sorting through information,
Yeah.
recognizing faces, understanding language.
Oh, effortlessly.
It seems so easy for us.
Right.
How did they even begin to approach that with computers back then?
Well, their initial approach relied heavily on logic and rules.
Logic and rules.
Like, imagine programming a computer to recognize a cat.
Oh,
But you have to define every single rule about what makes a cat a cat.
what?
Pointy ears, whiskers, a tail.
Okay.
It's a lot.
Sounds incredibly tedious and honestly prone to errors.
You're absolutely right.
Yeah,
It was far too limited.
right.
This approach couldn't handle the complexity of the real world.
Yeah, like a cat can look completely different, depending on the breed.
Exactly.
See, so
Lighting, trying
Okay.
to account for every possibility with rigid rules.
Yeah.
Nearly impossible.
So where did they turn for inspiration?
Nature, of course.
Right.
They started looking closely at the human brain,
Makes sense.
specifically at neurons.
Those tiny information processors.
Yes. The brain's very own mini computers.
So they were trying to replicate these neurons artificially.
Precisely.
Right.
In 1943, Warren McCulloch and Walter Pitts,
Oh,
a neuroscientist and a logician,
on pair.
proposed a simplified mathematical model of how neurons process information.
So this model was like a blueprint
Exactly.
for understanding how these tiny neurons work together.
In this vast interconnected network.
Yeah.
Exactly.
So that was a crucial first step.
It was.
Then in 1949, Donald Hebb presented a groundbreaking idea.
Yeah.
He said that learning and memory arise from strengthened connections between neurons that are frequently activated together.
That's right.
Neurons that fire together wire together. I've heard that saying.
It's a classic.
It's amazing that this concept from 1949 is still relevant today,
I know, it's incredible.
even in the way we design artificial systems.
It really is.
So Hebb's principle,
Yes.
the simple,
Simple but powerful.
forms the bedrock of how many artificial neural networks learn today. It's
It's
all about adjusting the strength of connections based on experience.
just like our brains do.
Fascinating.
Yeah.
And that's where our Nobel laureates step onto the scene, right?
Exactly. Each brought a really unique perspective.
Yeah.
John Hopfield, a physicist,
Okay.
approached the challenge through the lens of, physics.
So not just a computer scientist
Yep.
dabbling in neurons.
Not at all. He was already a giant in biological physics.
Really?
Yeah, he had made significant contributions
Wow.
to understanding how electrons move in biological molecules,
Okay.
even how cells correct errors during chemical reactions.
It's amazing how much these fields overlap.
Right, it's remarkable.
Okay, so how did this physics background lead him to artificial neural networks?
Well,
Seems like quite a leap.
it might seem that way, but there's a connection.
Mhm.
You see, in the late 1970s, Hopfield became captivated by this idea
What idea?
that complex behaviors like memory
Okay.
could emerge from large networks of relatively simple units.
Interesting.
This really resonated with his work in physics,
Okay, I see it.
where simple interactions between atoms can create really complex materials.
Right.
He even left his position at Princeton
Oh, wow.
to join Caltech.
Big change
He needed access to more powerful computers.
for his research.
Exactly.
Sounds like he was onto something big.
He was onto something groundbreaking.
What happened at Caltech?
Well, in 1982, he unveiled his network model,
Okay.
directly inspired by his understanding of magnetic materials
Okay.
and their atomic spins.
Interesting.
So imagine a grid of tiny magnets,
Okay.
each one representing a neuron in this network.
I'm picturing it.
Okay.
So these magnets, how do they actually store memories?
This is where it gets really cool.
Right.
Just like magnets align themselves to minimize energy,
Right.
Hopfield's network used a similar energy-based approach to store patterns.
How so?
Think of it like a landscape with valleys,
Okay.
and each valley represents a stored memory.
Okay.
Inputting a distorted image is like dropping a ball onto that landscape.
I'm with you.
It rolls down to the closest valley and reconstructs the original memory.
Wow, that's such an intuitive way to think about it.
It is, isn't it?
Even with errors or incomplete information,
Yeah.
the network could still retrieve the correct memory.
Exactly. It was a game changer.
It really was.
Hopfield's work demonstrated the power of these simple networks
Yeah.
to perform complex tasks like pattern recognition and error correction.
Amazing.
And this is where Geoffrey Hinton enters the picture.
Right.
With a background in both experimental psychology and AI,
Okay.
he was incredibly inspired by Hopfield's work.
So did Hinton focus on how machines could store information?
That's a great question.
Or was he more interested in how they could learn and adapt?
You're spot on.
Okay.
Hinton dove deep into that question.
Okay.
How could machines learn like humans,
Yeah.
not just store data?
Right. Learning from experience.
Yes, adapting to new information.
That's fascinating. What was his approach?
Well,
Did he draw inspiration from biology as well?
he did,
Okay.
but his journey took an unexpected detour
Really?
into the world of statistical physics.
Statistical physics?
Alongside Terence Sosnowski,
Okay.
he found inspiration in the study of systems with countless interacting parts,
Okay, so like what?
like the trillions of gas molecules in this room.
Okay, I have to admit, I'm not seeing the connection to neural networks yet.
Okay, yeah.
How does gas relate to all of this?
It's about focusing on the overall behavior, not the individual parts.
Oh.
In statistical physics, instead of tracking every single molecule,
Okay.
we're interested in properties like temperature and pressure.
Right.
Makes
Sure.
sense. Similarly, Hinton's work wasn't about micromanaging every single neuron,
Okay.
but rather understanding how they behave collectively as a network.
So instead of individual neurons,
Yeah.
he focused on the network's overall learning process.
Exactly.
That's pretty innovative.
Yeah.
What did this new type of network look like?
This led to the development of the Boltzmann machine
The Boltzmann machine.
in 1985,
Okay.
named after physicist Ludwig Boltzmann,
Another physics giant.
whose work was fundamental to their approach.
Two physics giants inspiring a new era of computing. I love it.
It's a fascinating story, isn't it?
But how did this Boltzmann machine actually work?
Imagine a network with two types of nodes.
Okay, two types of nodes.
Visible nodes, which receive the input data, like images,
Okay.
and hidden nodes representing the complex features and patterns within that data.
Okay.
It's like the visible nodes are our eyes taking in information,
Right.
and the hidden nodes are our brains making sense of it all.
That's a fantastic analogy.
Right.
So how do these nodes learn?
The network learns by adjusting the connections between these nodes, based on the examples it's fed.
So it's learning by example.
Exactly.
Okay.
The Boltzmann distribution, a concept from statistical physics,
Okay, back to physics.
helps the network find the most probable patterns in the data,
Even if the data's messy.
even if it's noisy or incomplete.
That's
But
incredible.
it's pretty amazing.
It's amazing to think that a statistical distribution from physics could help a machine learn to, say, identify a cat in a photo.
It really speaks to the power of cross-disciplinary thinking.
It really does.
However, while groundbreaking,
Okay.
these early Boltzmann machines faced a significant hurdle.
What was that?
They were computationally expensive
Okay.
and difficult to train on large data sets.
So they were ahead of their time.
Definitely.
But I'm guessing this isn't where the story ends. You're right, it doesn't end there. Hopfield and Hinton may have been a bit ahead of their time.
They were onto something big, though.
Yeah, their work wasn't over. It was like they handed the world blueprints. Blueprints. For a supersonic jet. But the engines weren't powerful enough.
Perfect analogy.
They needed time to reach their full potential. And a lot more computing power.
Exactly, a lot more computing power. What changed?
Yeah, what did change?
Yeah.
How do we go from these early networks to the AI we hear about constantly today?
The explosion of data and computing power in the 2000s
Okay,
led to deep learning.
there it is.
We suddenly had these massive data sets, images, text, you name it,
Wow.
and the processing power to actually make sense of it all.
This is when the field really took off. And Hinton, he was a major player in this whole deep learning revolution too, wasn't he?
Oh, absolutely. He had a pivotal role.
What did he do?
He realized by taking these simpler networks, like the Boltzmann machine,
Okay.
and stacking them on top of each other,
Okay.
creating these deep neural networks.
Deep neural networks.
Where you could tackle much more complex
So
problems.
instead of one layer of artificial neurons,
Right.
we now have networks with tons of layers.
Yeah.
Each one building on the last.
Building on the last to extract higher level features and patterns.
Wow, it's like building a skyscraper.
Exactly.
You suddenly have so much more space to work with.
You got it. And the scale is mind-blowing.
Okay.
Hopfield's early network
Yeah.
had only 30 nodes.
30.
Today's language models,
Okay.
like those powering advanced chatbots,
Yeah.
have over 1 trillion
A
parameters.
trillion.
Imagine each connection in this massive network has a tiny knob you can adjust. Those are the parameters.
It's a lot of knobs to adjust.
It's really incredible.
It is no wonder these deep learning systems are used in everything,
I know, it's amazing.
from medical diagnoses to self-driving cars.
It really is incredible.
And we can't forget their impact on science.
Right.
Artificial neural networks analyze data from the Large Hadron Collider,
Absolutely.
predict the structures of proteins,
Yeah.
and even design completely new materials.
It blows my mind every time I think about it.
It's amazing how this technology has come full circle,
Full circle.
originally inspired by physics, and now pushing the very boundaries of physics research.
It's incredible, isn't it?
What a journey from understanding the human brain
Right.
to revolutionizing countless fields.
It's amazing.
Artificial neural networks, that's quite a story.
It really is.
We've gone from those early days of computers that could barely recognize a pattern
Barely recognize a pattern.
to systems that can process information on a scale we barely thought possible.
And a lot of it comes down to that interplay between different fields.
Physics, biology, computer science.
Physics provided the spark, biology offered the blueprint,
Okay.
and computer science gave us the tools to build.
It all came together.
It did. And the future, who knows what breakthroughs we'll see thanks to this remarkable technology.
I'm excited to find out.
I am too. It's an exciting time to be curious about the world of AI.
It really is. That's going to do it for this deep dive into artificial neural networks.
Until next time.